Today we'll be taking T-Notes on 10.2, Part 2, Field at Work. We will be discussing escape speed, orbital motion, and orbital energy. Let's begin. So imagine that you're throwing a ball into the air. It would fall to the ground. What would happen if you were to throw the ball harder? Well, it would go higher and then take longer to return, but it would still return. How fast would you have to throw the ball so that it doesn't come back? This requires you to go to infinity or to escape the gravitational field of the Earth in order to have the ball completely escape. At infinity, remember that the gravitational energy is given by this equation here, which is E sub p equaling negative g, this is the gravitational constant, times the mass of the first object times the mass of the second object divided by the radius between the two objects. And this is where the gravitational energy is equal to 0 when r is infinite. Energy conservation tells us that the total energy must therefore have 0 energy to start with if it is to escape the Earth's gravity. So the total amount of energy is the kinetic energy plus the gravitational potential energy, and that this is set to 0. Understanding this will help us to determine the speed of an object. Escape velocity is the speed that is needed for an object to escape another object's gravitational pull. We know that the kinetic energy plus the gravitational potential energy equals 0. We also know that the kinetic energy is 1/2 mv squared. The gravitational potential energy is equal to the negative g, which is the gravitational constant, times the mass of the Earth times the mass of the second object, divided by the radius of the Earth. And that is set to 0. We can then solve for v, which would help us to determine the escape speed. And so that is v sub escape, and that's ESC equaling the square root of 2g, the mass of the Earth, divided by the radius of the Earth. Here's an example for you to try. Find the escape velocity for an object and the Earth. The Earth's mass is 5.98 times 10 to the 24th kilograms, and the radius of the object to the Earth is 6.38 times 10 to the 6th meters. Stop the video and start it back up when you're ready to see the solution. Okay, so we're going to be using the escape velocity equation, and when we plug everything in, and remember that you have the g, which is the gravitational constant, and you plug your other information in for the mass of the Earth and the radius, we are given an escape velocity of 11,181.966 meters, which is also 11.2 kilometers per second when you take into account how many significant figures. This means that in order to escape the gravitational pull of the Earth, the object would need to have a speed at least 11.2 kilometers per second in order to escape. Remember topic 6 and how we were introduced to the idea of how far you could launch an object that would result in the object following an orbital path around the Earth? And we talked about how far you could kick a dog in order to send it into orbit. The more force that you kick the dog, the further that the dog will go. However, gravity of the Earth is greater and will continuously pull on the dog and send it back to Earth. You would create even more force to create a higher speed and more force, and the gravity is still great, until eventually the dog is in orbit, and this is assuming that there's no air resistance. It continues in an orbit as it's continuously falling, but it never gets back to Earth. The force that is keeping the object in motion is the gravity, and that is called the centripetal force. Orbital motion is what we're discussing, and we know that with orbital motion, it is true that the centripetal force is equal to that of the force of the gravity. So we know that the centripetal force is equal to mv squared divided by r, and that the force of the gravity is equal to g times m, and these are the two masses of the objects, divided by r squared. When we solve for v, we get v sub orbit equaling the square root of g, the gravitational constant, times m sub e, which is the mass of the Earth, divided by r. Objects that are orbiting have both kinetic and potential energy. The object is moving, therefore it has kinetic energy. The object is also positioned at a certain height above the ground, thus giving it potential energy, gravitational potential energy. The total amount of the energy then would be the kinetic energy plus the gravitational potential energy. We know that the kinetic energy is 1/2 mv squared and that the gravitational potential energy is negative gm times m divided by r. If we move v squared over by itself, then we get g times m divided by r. Knowing that the kinetic energy is 1/2 mv squared, we can just take this gm divided by r and plug it into this equation here, and that would give us the kinetic energy equaling g times m of the second object divided by 2r. This is our kinetic energy. So when we plug gmm divided by 2r in for kinetic energy and subtract the gravitational potential energy, which is here, we get this equation here. And when we use simple algebra to add these two values, then we get the total energy of an object in orbit as being negative g times m of the second object divided by 2r. You can use this equation as it is. However, you can also go one step further and realize that gm times m divided by 2r, which is this right here, is the kinetic energy from up here, except that it carries a negative value. Because we know that kinetic energy is 1/2 mv squared, and we know that the total energy is the negative of that, then we can just say that the total energy is equal to negative 1/2 mv squared. Now that we have a better understanding of orbiting objects and escape velocities, we can briefly talk about how the speed at which an object is going will determine the shape of its path. If the velocity of the object is less than the escape velocity, then the orbit will follow a path that is either circular or elliptical. This is a closed orbit, and the object will repeat this orbit and this path unless another force acts on it. There is no added work that is needed in order to stay in orbit. In fact, here's a little bit of information. To achieve a circular orbit, an object must move at 71% of the escape velocity. Now, if the velocity equals the escape velocity, then the object will follow a parabolic path. If, however, the velocity is further increased to a speed that is above the escape velocity, then the object's path will look like a hyperbola. The orbit is then said to be open. The smaller object will escape and does not return. Okay, there are two practice problems for you to do. This is the first one, and the second problem has two parts. Please have the TNOTES and the practice problems completed, and be ready to use this information in class next. Thank you for watching.